Should I just start or what? Okay. Since I'm on stage already, so I think I'm going to start anyway. So good afternoon, everyone. Uh, I'm sure that I cannot see you guys, but I'm sure that you guys can see me fine, and I'm very happy to be here. Okay. So my name is Faisal. Faisal Rohmat. You can call me Faisal. I'm glad to be a part of this winter conference in this AI for Flood session. And today I'm going to share about the challenges and capacity building in AI based flood resilience. Let's go to the next slide. Okay, so this is basically my profile. I'm working at ITB in the Faculty of Civil and Environmental Engineering. Um, but more importantly, I'm doing AI, floods, and also I'm working closely with the international community in flood management, flood risk designs, and also AI research. Next slide. Okay, so I want to start. Can we go to the next slide, please? Boom. Okay, I want to start with this, with a not so sweet fact about floods in Indonesia. So we have in 2021 alone, Indonesia recorded more than 5,000 disasters every year, and one third of these events were floods. That is 1,700 of flood events every year. And with this figure alone, we can say that floods have become not only more frequent, but also unpredictable. Okay, and on the next slide, please, we will see that these are the distribution, the spatial distribution of the floods. Most of the floods in Indonesia are in Java, where most of the people are. Okay, next slide. And this is an example of how we manage flood in Indonesia, or how we experience flood, I should say, experience flood in Indonesia. In one of the most interesting figure or a picture for us was the 2013 flood in Jakarta. You can see the bottom right corner. On the bottom right corner, there is Indonesia's former president, President Yudhoyono, with the foreign ministers and many of his officials. What do you say? Melinting celananya, ya. So they roll their pants and walking uh, on the flood. So this is interesting because that was one of the most severe flood happened in Jakarta, the capital, and it even reached the presidential palace. So what I want to say from these slides is that floods in Indonesia are serious problems, but then we also have other problems of the lack of complete data set for rainfall, for example, river measurement, not only in terms of river geometry, but also in terms of flow. Yeah. So we are still building on that database, but the problem is present, but the problem is actual. The question is, how do we manage to solve this? Next slide. Okay. One approach is to have a modeling approach. Yeah. So these are the flood inundation modeling that we work on. For example, on the left hand side is the flood modeling in northern Jakarta, around the Ancol area. And on the right hand side is the flood modeling in Bandung, in Citarum River. As you can see here, to help us understanding the floods, we can use modeling. And on the next slide, we can also assess the what if scenarios. Yeah. For example, the left one is the modeling before intervention, and on the right hand side is the modeling after intervention. For example, what if we close the leaks on the riverbanks? What if we make a tunnel for drainage and also connect the smaller district drainage to the river pumps, for example? With this, we can assess the what if scenarios. Also, on the next slide, we can also check with the actual data set. Yeah, for example, here on the left hand side, we compare our modeling with actual flood inundation information gathered or collected with the local people. So we calibrate our models using the information gathered from the location. This modeling approach is very good. However, it is very slow. In some cases, or in most cases, we need information about flood as soon as possible. Yeah. But for example, to build this kind of models, we really need to collect the data sets, collect the topography, collect the rainfall, and then do modeling, and then wait for the model to run. For example, in a few hours or maybe even days. But we really need to answer, or we really need to get the answer as soon as possible. If not today, can we get the answer yesterday? Okay, let's see to the next slide. Okay, next slide, please. Okay, there you go. So the model that I just presented is called the numerical model. So it's basically we use physical laws that converted into numerical approach, and then, for example, here we use satellite data, convert it into calibrated rainfall, convert it or calculate discharge, and then model the water level. It is accurate but slow. There is another approach, which is the AI-based or machine learning-based approach, which we can use straight directly from the source data, for example, from satellite data to water level. This is a more recent approach, but also it relies also on the availability of the input and the output data, both in terms of completeness and quality, which we will talk about later from the presentation of Hazel and also from Jonathan and Anissa. Yeah. Okay, next slide. This is the example of our lab-proven model. Yeah. So in here, we use the LSTM machine learning approach to predict river discharge, or more accurately, river elevation or height, yeah, using satellite data. As you can see here, we are not only using current rainfall, current satellite captured rainfall, but also information from the hours before. Yeah, T minus 1, T minus 2, up to T minus N. And here, we can prove that it does work. Yeah, with some catch, of course. And the most important catch is it will be as good as the input data. Okay, that's one catch. And on the next slide, please. The second catch is Okay, next slide. Boom. Okay, can we go to the next slide, please? Now, there you go. Yeah, okay. So the second catch is any kind of technology is as good as the human resource inside it. Okay, so as we can see here in our water management industry, yeah, in this a very complicated chart, in the very middle of it lies the water industry workforce. It's the people. So first challenge about the AI building capacity in AI based flood resilience is the technology itself. How good are the data? Can we make a scalable platform to analyze the AI and present the information as wide as possible? And also, can we build people? Can we build the people to be ready for the AI era? Yeah, AI era. Next slide, please. So we really need to educate water people. Yeah, the students need to be educated not only in terms of technological knowledge, but they have to be also adapt towards the development of AI. Yeah, because AI is basically just a tool, but the knowledge and wisdom is the property of us, property of human. Next slide. How do we build those people? On the left hand side, left top, we build the students, we equip the students with the skill of computing. For example, in our curriculum, from the very first semester, we teach the student to work with data to program Python, for example. This applies not only in the computer science department, but also in the engineering department, in civil engineering, or in my case, in water resources engineering. Even in the biology department, we teach them how to code. Yeah. On the top right side, we also educate the students not only in terms of class knowledge, but also about the field knowledge. We met them with the people on the field who experience floods. On the left bottom, we also met them with the officials from, for example, this is from the Ministry of Public Works, to see how the nation managed the floods. And on the bottom right corner, it is never too early to introduce the importance of managing water and also introduce them to computing. It's never too early. Teach them as soon as possible with a simpler way. On the next slide, please. Okay, those are just some of my pictures. But basically, we also do research to make the technology more accurate and more applicable to our case. And don't forget to make a good networking like this winner event. Yeah, let's go to the next slide. So I just want to conclude my talk with that. We will talk about more detail about the importance of good data quality, how to make observation more democratized and more available to everyone. It's going to be a talk from Hassel. And then we will also talk about the example of a scalable platform for AI-based flood risk warning. Yeah, and also we'll talk about making this kind of information more reachable to general public. And that's it. So I want to end my talk with saying that water is the source of life, but it can also be a big problem, yeah, big destruction force, and it is our responsibility to manage it. Thank you very much.
Hello, everybody. I hope you can hear me. I also see that the slides are coming up. I hope that somebody can help me with moving to the next slides. My name is Hessel Winsemius. I already was introduced a little bit by Pak, and but I can say a little bit more about myself. I've been working with Deltaris for a long time in the Netherlands as a senior hydrologist, and since November, I'm full-time working for my own company, and the company is called Rainbow Sensing, and I focus on flood and discharge and water level observations of rivers and streams, and making the technology for that more accessible to a larger group of end users. And so, therefore, also the title of my presentation is Local River Monitoring Sensing Services with Cameras. So I work with cameras, but the word local here is also quite important. So it's not my intention to to do international river monitoring, meaning that an international group of people can provide services locally. But I want local people to offer services locally in their own environment, and I'm trying to facilitate that by creating new methods and making them available. So you'll see also that logo on the bottom right in my presentation a lot. It's Open River Cam. That is the software environment that I'm creating for this that enables sensing rivers with cameras. Next slide, please. I'm not sure if I can move myself. Is somebody? Yes, thank you. Okay, so Faisal already introduced a little bit what the relevance is. So I mentioned discharge monitoring. I will focus also a little bit on discharge in this presentation. Now, why is discharge important to know? So, for instance, discharge statistics, the maps that you see here, they cannot be created if you do not know the statistics of discharge in a certain river. So, if you want to know how often the picture on the right appears, how often that happens, you have to understand how often the driving force to this flooding occurs. And that is the discharge. Eventually, that is the driving force to it. And that creates then high water levels downstream, etc., etc. And also for flood forecasting, for instance, if you want to forecast a flood, and knowing the upstream discharge can already give you a very good skill downstream a few hours ahead in time, typically. And it's basically really the travel time of that water towards the place that you want to forecast for that then provides you that skill. And also for design purposes, if you want to design a culvert or a bridge or some other infrastructure, if you want to design a city, you have to understand the risks and therefore also the probabilities of certain floods occurring. Then discharge is very important to know. Next slide, please. So the question is it easy to do? Please, next slide, yes. So in fact, no, it's not. So while monitoring a water level is nowadays a little bit less difficult, monitoring flow, so really the amount of water passing through a certain section of a river, is actually quite hard. So you need to do field work for it. You need to go into the field. It's sometimes in remote places. It can be hazardous to people and equipment. So if you have to often go into the water with the equipment. Now, during high water, that can actually be dangerous. And also things like wildlife can be a problem. But yet, as I said, it's very important to have these observations as you want to measure for water use, for monitoring and forecasting floods, inflow and outflow of reservoirs, designs of bridges, levees, nature-based solutions, etc. And so really it's that's the Dutch expression, meten is weten. is really important. So mate is weten in English is what you cannot measure, or sorry, what you can't manage, what you cannot measure. So measurements are really critical. But the nice thing about cameras is with cameras and I will show that in this presentation, you can actually observe rivers very well without actually touching the water, without even needing to go exactly above the water, let alone standing in the water with instruments like what you see on the left picture. Next slide, please. Next slide, yes. Thank you. And can you perhaps click on unless I can do that myself, on the black image? That should be a video that should be playing now. It's not working. It cannot be played. Okay, that's unfortunate. The idea was that here on the right side you would see a video of a stream with water passing from the left to the right. So observe with the camera. So I cannot show that now, but maybe we can then go to the next slide because that also shows it a little bit. I think that's a better choice then. So this is another, it's a still, but it's actually a still taken from a video from a stream here in the Netherlands. And so you have to think a little bit, so how do we actually do that with cameras? Well, we do it in a very similar way as what my Professor Savanaye, that you saw in the previous picture, he was my supervisor during my PhD. He also told students like, okay, if you want to make an estimate of the stream flow, what do you then actually do? You go stand on the side, you try to figure out more or less what could be the width approximately. Well, given the width, and geomorphologically, usually the depth is about 1/20th of that. And then, of course, then you start to look at, okay, well, how fast is the border actually moving? So you look at the river, and you try to find patterns in the river that you can follow, or stuff, debris if it's flowing faster, or bubbles or eddies, or something that moves along, that it vects along with the stream velocity. You try to find that and then make a guess how fast that goes. Is it 0.5 meter per second or 1 meter per second? And then when you know that, you have an estimate of the width, the depth, and the velocities in the stream. You can integrate that and make a rough, if you look at my finger in my mouth, it's a rough estimate of the amount of flow in cubic meters per second. Now, if you think about that, if we can do that with our eyes, then computer software combined with a camera, if you go to the next slide, please, we can see that. Then a computer program with a camera taking videos can actually do that automatically. And here you can see that. And there's a few things then that the computer program needs to be interpreting, very similar to what we do with our eyes. And that is really the perspective that we look at. So that place further along, where I'm trying to figure out what the velocity is far away. So it looks like it's slower, but it's actually the same velocity. And the closer pixels are, they represent a smaller distance. So all those things have to be interpreted. But once you've done that, a camera can actually automatically make these estimates of velocity that you see here expressed in this example image. It's an augmented reality of the velocities on top of on the surface of the water. And combined with knowledge of the depth, which you can measure beforehand. So you can do that when you install the camera. You do that once, and then you move away. So if you know the water level, you have a video, you can actually continuously record discharge. In this case, the discharge was estimated, what you see here on the top right, to be 1.23 cubic meters per second. So that is sort of the working principle. Next slide, please. I'm going to move a little bit faster now. I think that this is quite clear. So now the cool thing is that since next slide. So since just a month or so, WMO, the World Meteorological Organization, actually recognizes image-based methods to be a low-cost, efficient, and non-intrusive alternative to measure surface velocities and calculate discharges. And the cool thing is that where traditional discharge observation methods, you would actually have to go out in the field with instrumentation, etc. With this technology, you can have a camera automatically record videos and transform them into flow. So we can actually, rather than maybe once a month revisit a site and take a discharge measurement, we can do this every 15 minutes now. And also the World Bank is really advocating now for affordability of monitoring systems for design and flood early warning. So fit for purpose and fit for budget. And the nice thing about this technology is that cameras are so omnipresent. We even have cameras in our smartphone. Everybody has a smartphone with a camera, that they are also very affordable. So it's actually a very pretty much affordable technology. Next slide, please. So the question is there applicability thinkable in Indonesia? Well, we're now trying out to sort of leverage this technology in Lusaka, Zambia. And what you can see here is we see here that on the top right, a recently installed site that continuously takes observations every 15 minutes in the city. And it's the nice thing about an urban environment is that we can also look for a flexible place to install the camera, in this case behind a wall perimeter, which also protects it from vandalism. So that is quite a nice advantage if you move into urban environments. And I would think that in Indonesia you have many cases where this can also apply. You have those urban environments as well. You don't have to place this on a bridge or an open area necessarily. There are many smaller fleshy rivers in Indonesia, and it's a nice non-contact, non-intrusive and safe method therefore. And also the maintenance is very low. We have a camera system in the Netherlands that we run as a pilot, and I have not visited that place for more than a year, and it's still running. Next slide, please. So now a little bit about Open River Cam. So I mentioned that at the beginning. So I explained the technology, I explained the suitability also for Indonesian conditions. What is Open River Cam? Actually, it's a software system, free and open source, that my company is creating that allows you to actually do these observations autonomously, automatically. You can do that. You can do the processing with small devices on the site or in the cloud. And we have a dashboard and API that can sort of centrally collect all the observations from multiple sites if you're a bigger organization. And it's free and open source with the idea that local people can start to develop their own services around this, perhaps with their own clientele, with their own clients in their own environment. So I'm not in the position to do that myself here from the Netherlands. Local people should do that. And by making this software free and open source, I hope to also create an enabling environment for that. Next slide, please. So just a few examples of what you can then reach. So what we did we did a small test for about a month in Switzerland together with a partner institute, Fotrec. And we installed a camera. You can see here an example on the right side that was collecting observations, I think, every half hour. And within a month, we were able to collect a relationship between water levels and discharge with a significant range. You can see that the discharge range is between 40 cubic meters per second in the graph with the black crosses, between 40 and 140 cubic meters per second. So within 1 month, we collect this relationship, which is typically the work of tedious observations with instruments going into the field, which might take you several years. And if the profile changes, you actually have to redo that analysis. Next slide, please. So what does it involve to set up a site? This also goes a little bit more into how manageable would it be if somebody's interested to actually set this up. So here you see an example of a setup that we made with the Trans-African Hydrometeorological Observatory in Dar es Salaam in Tanzania. And so what you see here on the left side is that it really consists of a small device doing the processing, and that communicates to our live API. And then you need a camera, a small camera setup, which you can also see outlined here. A small battery, 100 watt hours is really sufficient. You can even do it with 70 or 80 watt hours, and that should be sufficient. It can run on 12 volts. You can also run it on 24 volts, of course, if you convert it eventually. And yeah, typically now we use a Raspberry Pi, so that's a small microcomputer, single board computer. To do the edge processing, but it's not constrained to that. So software is hardware agnostic, so you can also install it on other devices if those are more prominently available in your environment. Now, the cool thing is if you have a reasonably well-defined channel, like here, we have a nice concrete line, you can also detect the water level optically, which means that you do not need an additional instrument that hangs above the water to measure that. You can do that, it's more accurate, but if you do not have the ability to do that, you can also optically measure it. And then next slide, please. Yes, and then so really the work that you have to do to set this up is find a suitable site, set up and aim a camera, for instance, on a mast, like what you saw in the previous slide. Then you have to perform some typical surveys with a good GPS set, or with other, or maybe a total station or something that you can measure 3D coordinates with, including also a cross section, so the profile of the stream. You do that once and you fill it into the software, you configure the camera system, and then basically you leave everything behind, and then the camera does the rest of the work. And then you do not have to return to the site unless there's something really wrong, or if you're really unlucky, there could be vandalism issues. We could discuss that also. But if not, if you have placed it in a secure location, typically you do not have to come back for a full season. Next slide, please. So how do I make my money? That's an important point. I have to survive, of course. So what we're going to do is to provide sort of service contracts with which you get either an image that you can flash yourself on a device that you create yourself. But we're also going to make a plug and play box called the PT box. We do that with our partner Photrack. That has the software included, and you will get also support hours within the first year for that. And it's really for a relatively modest price, so that you can start quickly. But the idea is that once you get the hang of this, you could decide to not get a plug and play box and build it yourself. Or for instance, or even say, okay, I'm going to go full open source. I don't need your support anymore. I'm independent now. So the trajectory should be start simple and quick, with some costs, and I can provide training, etc. And eventually you can manage things yourself. Next slide, please. I'm almost through. So we're trying out this model, this business model in Zambia at the moment. We have a local company called Local Devices Technologies, and they are now in the position to develop their own services for their own clients in Zambia. Now my question is a bit open question. Would such a model also work in Indonesia? Next slide, please. And I think that's it. So thank you.
Okay, thank you. Good afternoon, distinguished guests, fellow researchers, and resilience leaders. It's an honor to share before you today. I would like to begin with simply truth that floods are no longer distant threat. They are immediate, recurring, and deeply personal, especially for cities like Jakarta. We combine real-time hazard feeds, community-level data, and secondary timelines into unified interface, not for the sake of technology alone, but to empower decision makers, planners, and responders with clarity and speed. Our goal is simple: to shift from reactive recovery to proactive resilience. And we believe that start with collaboration across discipline, across border, and across sectors. That we've done with Airlaga and rainbow sensing. Let's build the flood resilient future together, grown in science, powered by AI, and driven by shared purpose. Maybe next slide, please. Before we deeper into the flood resilience, I want to share about the moment to show you the broader foundation behind this analytics. What you see is our AI portfolio, six distinct products that related the algorithm, the model, the architecture to build this application. Each of application is built to solve the real world problem. From the remote health diagnostic, banana ripeness detection to financial analysis and corporate governance. This tool reflects our commitment to precision, scalability, and impacts. This means our model is adaptable, architecture is modular and scalable. So this application currently have solution to our small clients. So we move forward. I invite you to see this analytics not only a fraud prediction tools, but a part of larger movement to make AI work for people and for future. Next slide, please. Now, let's step back and look the how we build architecture behind our solution. I was try to see this application based on my point of view as the risk management. This framework is not just a technical diagram; it's also a roadmap for resilience. It integrates risk-based probability, exposure mapping, vulnerability assessment, and resilience modeling across time scales and geography. This implementation roadmap is equally critical. So we outline how to ingest data from weather API, infrastructure database. So we built decision support layers that deliver real-time alerts and forecasting. And we embedded governance tool, dashboard, performance metric, and stakeholder feedback. Next step, next slide, please. This image is familiar to many of us. Street turned into rivers, cars submerged, family wading through uncertainty. And yet, we know that early prediction could change this. Our application, developed by data and compiled with unified insight to deliver the real-time prediction that protect the futures, and to make that no community left behind when the next flood comes. Because climate resilience is not about infrastructure, it's about equity, foresight, and action. Next step, please. Okay. Currently, our application update cycles 3 hours and designed for the scale cross flood-prone regions. We integrate multimodal data, flood, and weather into the unified interface. This dashboard doesn't uh, show flood risk level, but it translates them into decision. For researcher, this living lab where the model meet the reality, but for expert, it will be precision tools where the threshold, timelines, and spatial intelligence coverage. And for the leaders, this is a small command center where decision is backed by data to protect critical infrastructure, prioritize the most vulnerable. Because climate resilience is not about the predicting food, but about preparing community and protecting the futures. Next slide, please. Next slide, please. Okay. We built the custom alerts and notification so that user can understand about the rainfall threshold and receive a real-time push update because timely information save lives. Second, we introduce scenario simulation that what if tools planners that respond can test mitigation strategies like the displacement and green zone development for the long-term strategies repairment and instantly visualize their impact. what is the impact and what the AI give suggestion to us for the next action. Third, we open the door for collaboration. This analytics includes community forum and developer API to foster innovation, transparency, and sharing learning. Next slide, please. Next slide, please. Okay, this slide highlights has three pillars to make very important for the flood resilient. First, prediction and forecasting. We deliver two 7-day flood timelines with interactive heat maps and zip code level precision. Second, monitoring and data visualization. We integrate real-time feeds and crowdsource upload to enrich our AI data analysis. This isn't static data. This is living intelligence that's shaped by community and sensor alike. Third, the robot risk management. Our impact dashboard have detailed report to help quantify exposure, vulnerability, and downtime. And yes, we built seamless linkage to ensure platform because resilience must include the recovery for the futures. Next step, please. Yes, this application is not about the technical solution, but also catalyst for the faster response. It built for the every people for the smarter planning and safer communities. We've seen about the 50% faster emergency response and early warning and real-time alerts. Our user-friendly design has ensured accessibility across language, device, and connectivity level. Whether you are in control room or on the ground, the interface intuitive, responsive, and ready. With scenario tools, we help reduce potential damage by 30 and 40% by enabling proactive mitigation and not reactive recovery. Next slide, please. As we close, I want to shift presentation into invitation. Flood resilience is not a solo mission; it's a shared journey, and this slide reflects to our next step. First, we focus on the building community. That means we connecting the students, researchers, and what we call maybe weather whisperers to woods to understand the pulse, nature, and the potential of the technology. Second, we opening the doors of partnership and contribution just with it through the Airlaga, rainbow sensing, and a new alliance that maybe we haven't imagined. We we're ready to go to co-create solution that scale. That we welcome question and discussion because resilience grow stronger when it's challenged, refined, and expanded by diverse perspective. And finally, this flag together Indonesia and Netherlands is not more than symbolic, but it represents commitment to global collaboration, sharing learning with mutual respect. So whether you are researcher, policymaker, technologist, or student, the role for you shaping the flood resilient future. Let's build together. Next slide, please. As a wrap up, I want to thank each of you, researchers, experts, and leaders, for your time, insight, and for your commitment to resilience. This session is not about the showing case but platform, but it also showcases but vision, where one data drive decision, communities shape solution, and collaboration across the border. From Jakarta to Netherlands, I hope this analytics inspire you to act boldly, build inclusively, and lead with purpose. Thank you. Together, we can shape the flood resilient for the futures. Maybe you can.
Oh, okay. So for Pak Muhammad Zaki, would you mind to share my screen? Yes. Okay. Okay, seems like we're supposed to wait for the presentation to be shared by the committee. Oh yeah, thank you. It's disappeared again. Okay, I think we're ready. Yeah, good afternoon everyone in Indonesia. And goedemorgen for iedereen in Netherlands. My name is Anissa Laila Rahmawati. I am a coastal and water resources engineer from East Java, Indonesia. Next slide. For over a decade, I worked in the Government Water Resources Agency, and I continued my studies in water and sustainable development at IHE Delft, Netherlands. And now, through Erlaga Studio, a new platform based in Delft, I'm exploring how we can connect science, data, and storytelling to make climate adaptation more inclusive and participatory. And my presentation today will explore how AI and the hydrodynamic models can complement each other in predicting and adapting to compound floods. Indonesia and Netherlands, both countries depend deeply on water, but face it entirely different ways. That's where our learning began here. On this slide, we can see differences between archipelagic cities in Indonesia and delta cities in the Netherlands. In Indonesia, especially along the north coast of Java, floods are frequent and compound, like rainfall, high tides, storm surge, and land subsidence interact and amplify each other. In some neighborhoods, subsidence exceed 10 centimeters per year, meaning that even normal high tides can flood the city daily. Meanwhile, the Netherlands face the opposite timescale. Cities like Rotterdam or Dordrecht are low-lying, but protected by advanced system of dikes and barriers. But still, sea level rise and river inflows pose new risks. So both countries face compound flood risks, urgent and frequent in Indonesia, but rare but catastrophic in the Netherlands. Next slide. Now, after seeing the contrast, here what connects both regions: compound floodings. Compound floods occur when multiple drivers, rainfall, river discharge, tide surge, or even subsidence overlap. Each alone might not be disastrous, but together they amplify the impacts. On the left, you see two simplified types: inland floods driven by rainfall and rivers, and coastal flood driven by tide and surge. But in real life, the system interact. This overlap is specifically critical in tidal river areas like Semarang or Rotterdam, where inland and coastal process meet. And special highlight here is the dike bridge. It's not the driver itself, but a sudden failure when combined pressure exceed design limits. We have seen this in history, like the one in the Netherlands in the North Sea, the flood in 1953. And that's why studying compound drivers and structural resilience together is crucial here. It's not only about how high the water gets, but when and how the multiple forces combine. And to simulate that complexity, we rely on hydrodynamic models. Next, next slide. And excuse me. Okay. So, physics-based models such as Delft 3D, HECRA, Sphinx are the backbone of flood analysis. They are trusted because they follow physical laws of mass and momentum, showing how water actually moves across land and structures. But there is a catch. These models are data hungry and computationally expensive. Running one simulation can take hours, making it difficult to test hundreds of adaptation scenarios like polders, mangrove, or zoning strategies. So while they give precision, they lack speed. And in an age where flood risks evolve daily, That's the gap we need to bridge. That's where AI begins to play its role. Next slide. So, if hydrodynamic models give us accuracy, AI gives us adaptability and speed. Think of as AI not as replacing physics, but as its partner. AI can also fill gaps, emerging satellites, sensors, and even community reports. And it can also detect compound flood patterns, recognizing when rainfall, tide, and surge overlaps to trigger early warning. And when combined, AI and physics creates flood models that are not only reliable but also real time. And in this partnership between science and speed, it's what inspired me to develop a more human-centered platform, Erlaga. Next slide. Okay, so after exploring AI potential, let me introduce Erlaga, which in Bahasa, air means water and laga means action. So it's essentially means water in action. The idea came from a challenge that I saw for many years. We have rainfall data, tide data, subsidence data, but they live in different systems. Communities and even local agencies cannot access them fast enough for decision. Erlaga is designed as an AI-powered platform that connects these fragmented pieces. And this platform focuses on three things. First, visualizing compound flood risks through intuitive maps, and then testing adaptation option like pumps, mangrove, or zoning through quick what-if scenarios, and then translating science into stories so communities can understand and use it. So it's being designed for municipalities, school, and community organization, anyone who wants to make water knowledge actionable. In short, Erlaga turns data into knowledge and knowledge into shared climate stories. Because adaptation works best when science, policy, and people move together. Next slide. Prediction alone is never enough. What truly matters is how we adapt. Both Indonesia and Netherlands rely heavily on structural measures like seawalls, pumps, and polder as the backbone of protection. Like in the Netherlands, the Maisland carrying is a global symbol, a storm surge barrier protecting 2 million residents of South Holland. And in Indonesia, we also have NCICD projects in Jakarta use a similar no-regret approach, combining seawalls, pumping, and social dialogue to protect the capital while reducing conflict. But these structures are costly and rigid, and alone they cannot guarantee resilience. That's why both countries now combine them with nature-based solution and governance framework. In short, adaptation is not just about defending against water, it's about living intelligently with it. Next slide. Next slide, please. Okay. So traditionally, adaptation planning has been physics-based and expert-driven. Models like Dev3D or Sphinx simulate flood behavior with precision, and planners use the result to design long-term strategies. Yes, it is trusted, but also slow and static. When AI enters the process, adaptation becomes dynamic. AI can rapidly screen hundreds of what if scenarios, merge satellites and local data, and visualize outcomes interactively. This hybrid approach doesn't replace experts, it expands their capacity. It allows adaptation plans to evolve continuously instead of waiting years for revision. And as Del Torres called it, this is like the next phase of adaptive pathways, where AI keeps plan alive under uncertainty. Next slide. Next slide, please. Okay. So where does this all lead? AI is no longer just a prediction tool. It's part of the adaptation cycle itself. The UNSCAP calls it a game changer for resilience, especially in data scarce regions. It helps connect the dots, linking global climate risks with local adaptation needs. But technology alone is not enough. Here, Utrecht University reminds us that adaptation must be human-centered, transparent, inclusive, and co-created with communities. And framework like RECC, Research and Action on Climate Change, show how AI can support adaptation through 4 stages: data collection, scenario simulation, pathway planning, and action implementation. And then when we combine physics for accuracy, AI for speed, and people for legitimacy, we move from prediction to adaptation to resilience. Next slide. Next slide, please. Excuse me? Okay, thank you. So, adaptation is not just about models, it's about connecting system. So here for Erlaga collaboration, both Google Flood Hub and Delphius are powerful, but for different reason. Next slide. Okay. Flood Hub is fast and global. This is an AI-driven platform forecasting river floods up to 7 days ahead. It is scalable but river-centric. It doesn't yet include tide, search, or local community data. Next slide. Meanwhile, here, Delphius, developed by Deltares in the Netherlands, it's opposite. It is trusted physics-based system used in over 70 countries. It doesn't predict from data. It's organized and automates hydrological models for operational forecasting. It's reliable but complex. It's designed for engineers, not for citizens. Next slide. Okay. Oh, yeah, that's where Erlaga comes in. Not to replace them, but to connect them. I think it should be like the animation here covering the table, but it's okay. We can continue. With Flood Hub, Erlaga could use API integration to ingest forecasts, add local data like subsidence and tides, and display them in interactive dashboard for Indonesian coastal cities. It turns a global system into a locally relevant picture and showing not just where floods may happen, but why and what to do next. Can we go to the previous slide? Okay, sorry for the animation that covering the table, but you can continue about how collaboration could work. And also with Delphius, the collaboration goes both ways. Erlaga can receive model result like rain, tide search via data exchange protocols and revisualize them into public dashboard and story maps. So think about it this way. Flood Hub looks at the world from above, giving us global reach. And Delphius looks deep inside the system, giving us scientific rigor. And Erlaga stands on the ground, bringing local relevance, turning all data into something that people can see and can actually use. And together, these three systems form a complete circle from prediction to planning and from planning to action. And that's how we turn global forecasts into local adaptation. Next slide, please. Okay, yeah. So how do we make this collaboration real? We start small with pilots and proof of concept. In 2025 and 2026, Erlaga and partners will run early pilots in the cities in Indonesia, integrating flood hub data with local tidal and subsidence information. And by 2026 and 2027, we aim to connect Delphi's workflow, creating a hybrid dashboard and validating them with local agencies. And by 2028 and beyond, the goal is to scale and institutionalize, establishing shared training programs, government buy-in, and sustainable operating models. So this is not just a research project, it is a pathway toward shared resilience infrastructures. Next slide. So, when we talk about AI in adaptation, we are not talking about replacing human judgment. We are talking about enhancing it. Climate risks are multi-driver and messy. Rainfall, tide, and subsidence interact unpredictably. AI helps us make sense of this complexity, scanning vast data sets, turning them into actionable insights. And in Indonesia, AI can help bridge data gaps, linking rainfall, tide, and subsidence data to test coastal measures faster. And in the Netherlands, it complements long-term hydrodynamics planning by running hundreds of what-if tests efficiently. The key principle is collaboration, human-centered AI combined with physics and policy co-design, creating adaptation that is locally just, data-informed, and scalable. Next slide. So as we have seen, the real power doesn't lie in one model or one tool, but in connection. Delphius brings precision and structure. So Google Cloud Hub brings global AI intelligence, and Erlaga bridge both, translating science into insight, stories, and collaboration that people can actually see and use. This partnership is more than data exchange. It's a bridge between Indonesia's urgency and Netherlands' long-term data expertise. And also, together with partners like JIS Analytics, ITB, and Rainbow Sensing, we can build an AI-driven, human-centered system that turn predictions into adaptation and adaptation into resilience. Seperti air yang selalu mencari jalannya, like water, we find our path. En samen vinden we onze weg naar veerkracht. Thank you. Okay, then we can go to the last slide. Yeah. So I think the time is up. Should we ask the committee that because we started the session quite late, maybe we can check if the committee said that we're gonna play the video from this analytic. Yeah, while waiting for the video to be played, is there any question for our speakers in the session 2? For Pak Faisal, Pak Jonathan, and Mr. Hazel, or maybe for me? If there is any question, audience can type the question in the chat in the right side of the screen. And now we're still waiting for the video to be played. And also your question if there is any. How many minutes do we still have? Maybe while waiting for the video and also for the question from the audience, if we still have time, can we invite other speaker to the stage? Pak Faisal, Pak Jonathan, and Mr. Hassel to be on the stage together, four of us. All of us, yes. Yeah, there's a nice video that committee want to play here from JIS Analytics. And we're still waiting for the video to be played. And yeah, from this session, actually, I really, it's an honor to be here speaking with all these experts, Pak Faisal, Mr. Hassel, Pak Jonathan, and learn a lot from them. And also from this session, it's not only just a session here, but we actually already developed preliminary, how we call it, collaboration to have a next project, like a follow up together, in which it can be like a workshop. It can be like also build a platform together. So yeah, actually before this event today, we already have like a 2 or 3 meetings. But Jonathan, is it right? 3 meetings, I think. Yeah, we already have 3 meetings together because we're really excited to be, like bringing the bridge between Netherlands and Indonesia, and also because Netherlands is, the biggest expert in water in the world. We learn a lot from them, and we're really happy also here to have Mr. Hassel that also bring the innovation with the remote sensing, with the rainbow sensing. Sorry, with the rainbow sensing, in which we also will have collaboration with Mr. Hassel together in Indonesia. And also, it's really nice to learn from Pak Faisal. Seems like from the committee saying that the resolution of the video is too large to be played in this platform. So maybe if there is any additional information or any feedbacks from other speakers, or maybe additional information for the audience here.
We have to, I personally say thank you for this team and sudden team, yeah, because yeah, I just meet them, yeah, less than 1 hours, and yeah, thank you for the winner to choose this is my session to elaborate between Indonesia and Netherlands. Yeah, I hope maybe we can see you in the future for the next collaboration. Yeah, maybe Pak Faisal have the closing statement.
Well, from me, I'm very happy to be here, and this is just the start. And we still have a lot of floods to manage, so hang in there.
Yeah, thanks
Thanks.
for all the audience. I saw that there were a lot of people online, so yeah, still very curious to hear thoughts about suitability in Indonesia or what we should change in our models. So if there's any follow-up that you think we should discuss, then please send me or us an email, and I certainly hope for a future collaboration. Thanks.
Thanks.
Thank you, Pak Faisal, Mr. Hassel, and Pak Jonathan,
Thank you,
and
Pak
for the all
Faisal.
audience. If you're curious and want to know more about all the stuff that we already talked in the session, you can just email us and also wait for the follow up. Stay tuned for the AI in adaptation tools and then bridging Indonesia and Netherlands together. Thank you so much, everyone, and
Thank you so much.
do
Thank you.
day.
Bye.
Thanks a lot. Tot